If I told ya there's a mathematical idea that lets us kind of peek into infinity? Well, that's exactly what we're exploring today, the limit. It's the foundational concept that unlocks the entire world of calculus, helping us understand the infinitely small and the infinitely large. I mean, think about that for a second. It sounds like a riddle, right? This question is the central mystery we're going to unravel in this explainer. It's all about how we can describe the idea of approaching with real mathematical precision. Okay, so let's just jump right in. Before we get bogged down in any complex formulas, we're going to focus on the simple, intuitive idea at the heart of what a limit really is. Picture this. You're walking down a long hallway. A limit doesn't care if you actually open the door at the very end. Nope. It's only interested in which door you're getting closer and closer to. It describes the tendency of your path. Now, for the more official definition you see here, let's not let it scare us. Let's just connect it right back to that hallway. Think of X as your current position in the hall, and A as the location of that door you're walking towards. Now, f of X could be anything that depends on your position. Let's just say it's the temperature at that exact spot. So L is the temperature you are approaching as you get infinitely close to that door. So that's the theory, but seeing is believing, right? Let's make this whole abstract idea way more concrete by looking at a real example of a function on a graph. Okay, check this out. This visualizes that journey perfectly. Just follow that blue curve with me. As our x value, that's our horizontal position, gets closer and closer to 2 from both sides, notice where the function is heading vertically. It's just homing right in on a y value of exactly 3. And this table here, it's just showing the exact same thing, but with raw numbers. Look at the values for x as they creep up to 2 from the left. You got 1.9, 1.99, 1.999. See how the function value gets closer and closer to 3? Well, the same thing is happening from the right. The numbers are literally squeezing in on that limit of 3 from both directions. All right, so that seems pretty straightforward. But here's where limits get really fascinating. What happens if the point we're approaching is actually missing? Yeah, this is a super common situation in calculus. Sometimes plugging a specific number into a function gives you an error, like division by 0. There's a hole, a little gap in the graph. So the question is, can we still talk about what the function is approaching? So take a look at this table. There's that blank space right at x equals 1 because the function is undefined there. But just check out the values around it. From the left, we're getting super, super close to 2. From the right, we're also getting closer and closer to 2. The trend is just undeniable, even with that hole right in the middle. And this brings us to a massively important point summed up perfectly right here. The limit could not care less what is happening at the point itself. It is all about the neighborhood, not the specific house. It's completely focused on the approach, which means, and this is huge, a limit can exist even when the function itself doesn't at that exact spot. But hang on, there's one more major twist to this story. What happens when the path you take to approach a point dramatically changes the outcome? This is called a step function. For all the negative numbers, its value is just 0. It's a flat line. But the instant we hit 0 and move into the positive numbers, bam, it instantly jumps right up to a value of 1. There's a clear break in the path. So let's look at our two paths. If we approach 0 from the left side, along all those negative numbers, our function's value is always 0. We call this the left-hand limit. But if we approach from the right side, along the positive numbers, our value is always 1, and that's the right-hand limit. And here's the final rule. For an overall limit to exist, the left-hand limit and the right-hand limit must be the same. Since our journey from the left ends at 0 and our journey from the right ends at 1, they don't agree. So in this case, the limit simply does not exist. End of story. So we've looked at approaching, we've looked at missing points, and we've looked at these different paths. But why is this so important? Let's zoom out for the big picture. This quote from the source material is really the key takeaway. Everything in calculus, from finding the slope of a curve at a single point to calculating the area under it, it's all built on this one core idea of getting infinitely close to something. So, mastering the limit is like learning the first, most powerful move in a grand strategy game. It opens up a whole new world of mathematics. And that leaves us with the real question. It's not just what is a limit, but what incredible things can we now build with it?